We are now going to discuss whether a power series converges uniformly to the limit function in its interval of convergence. To do this, we need a general result about uniform convergence of series of functions. This is the popular Weierstrass M-test. Theorem, let Fn from, no need for AB, let Fn from S to R be a sequence of bounded functions. Suppose norm Fn is less than or equal to some Mn and summation Mn converges. Okay, then we have summation Fn converges uniformly. Okay, so what this is saying is, if you have a sequence of functions, now you're interested in whether the series summation Fn converges uniformly. If you could bound the norm of Fn by Mn and summation Mn converges, then it follows that summation Fn converges uniformly. And the proof of this for all the hype is rather trivial. This follows immediately from the definitions and Cauchy criterion for uniform convergence. So this is a rather straightforward proof. So even though this result is of primary importance, I'm essentially leaving the proof to you. We are at the last stages of the course, so it should be fairly easy for you to prove such simple theorems by now. In any case, please do this in detail. Okay, so now that we have shown, or rather I have left you to show this Weierstrass M-test, we can now try to see whether the power series converges uniformly. So recall that we have already shown that if summation an x bar n, a power series converges at some point r greater than 0, then it converges absolutely in the interval minus RR. So if you don't mind, let me just change this to x naught. It converges absolutely in the interval minus x naught. We have already shown this, and this was just an application of the comparison test. Okay, now I'm going to redo that proof now, because that will actually show uniform convergence when you ponder over the proof and see that the Weierstrass M-test is applicable. So let me state the theorem. Suppose the power series summation an x bar n converges at the point x naught greater than 0 in R, then for any closed interval minus a, which is a subset of minus x naught, we have that summation an x bar n converges both absolutely absolutely and uniformly. Note the very careful hypothesis. I do not claim that the series converges absolutely in the closed interval minus x naught x naught. That's not what the claim is. The claim is that in any closed subinterval minus a of the open interval minus x naught, we have convergence. And the reason why we have such a peculiar conclusion will become very clear when you look at the proof. The proof is mostly a repetition of what we have already seen when we saw absolute convergence. So let capital M be an upper bound for mod an x naught power n. Such an upper bound exists simply because the series converges at the point x naught. Because summation a n x naught power n converges, we certainly have an upper bound. So mod a n x naught power n is less than m. Take an upper bound like this. Okay. Now, if x is an element of the closed interval minus a, then as before, we apply the same argument. Mod a n x power n, which is equal to mod a n into mod x power n, is less than or equal to mod a n into mod a power n, which is equal to mod a n mod x naught power n into mod a by mod x naught the whole power n. Okay. Now this is going to be less than or equal to m times mod a by x naught power n. Because we have chosen this a to be such that minus a closed interval is contained in minus x naught. So because a is strictly less than x naught, we have summation m mod a by x naught the whole power n converges. This is just a geometric series. Now it follows immediately that summation mod a n x power n converges uniformly for x in closed interval minus a by Weierstrass's M-test. Excellent. What we have now shown is that whenever you have convergence at a particular point x naught, then we have convergence in all closed intervals that are strictly contained in minus x naught. Now you may ask, what happens if I consider minus r, where r is the radius of convergence? Recall, the radius of convergence is the supremum of all the values where the series converges. Okay. Now let me caution you that remark, it need not be the case that summation a n x power n converges uniformly in minus r. There is no reason to expect this to happen, especially in light of our proof methodology, but it's always good to see a concrete example, and the example is not too hard. Just look at 1 plus x squared plus dot. The familiar simple geometric series. We know that the radius of convergence is 1. But nevertheless, it is not true that this series converges uniformly to 1 by 1 minus x in minus 1, 1. This is not true. Please check. Please check this. Okay. So we only have uniform convergence with this peculiar restriction, but for all practical purposes, this is not really such a big issue. Okay. Now we come to one of the most interesting properties of power series, behavior of power series under differentiation. So this is going to be quite an easy proof, but I'm going to call it a theorem because it's so important. Let summation an x bar n converge with radius of convergence r greater than 0. Then the derived power series summation n equals 1 to infinity n an x bar n minus 1 also has radius of convergence r, and this series converges to a function f, to a function not f, function g, such that f prime equal to g, where f is the function summation an x bar n converges to. So what this theorem is saying is essentially that if you have a power series, then the power series converges to a function that's differentiable. Not only that, the derivative of the power series is nothing but the limit of the derivative of term by term derivative, the series formed by term differentiation of the original power series. Let's see a proof of this. Much of the hard work has been done when we showed the behavior of uniform convergence under differentiation. Okay. Now, suffices to show that this summation n equals 1 to infinity n an x bar n minus 1 has radius of convergence r. Okay. After this, the result is immediate by the behavior of power series under differentiation. Okay, if we can show that the series of derivatives converge to a function g, then that convergence will have to be uniform on all closed subintervals of minus r. Then you just apply the result that when you have the derivatives converging uniformly and you have convergence of the original series at one point, then everything happens. Okay, now let's see why the derived series, which is this, has radius of convergence r. Now, suppose summation an x naught bar n converges. What we are going to show is also assume x naught is greater than 0. We are going to show that if x is in minus x naught, then summation n an x bar n minus 1 converges, n running from 1 to infinity. This will do the job for us. This will show, in fact, this will show something stronger. I'll come to that. This will in fact show that the radius of convergence of the derived power series star is in fact greater than or equal to the radius of convergence of summation an x bar n. If you think carefully about this, you will get that if you can show that this happens, that summation an x bar n minus 1 converges, we will be actually showing something stronger than needed. We will then reduce to the case that the radius of convergence is actually just equal to r at the end of this proof. Okay, so we have to show that summation n equals 1 to infinity n a n x power n minus 1 converges. And we do the same thing. Let capital M be an upper bound of mod an mod x naught power n. Okay, we will also assume that x is not 0. Nothing to show if x is 0, so assume x is not 0 is fixed. Okay, note we are fixing x now. This will become apparent in a moment why we are fixing x. Now, modulus of n an x power n minus 1 is less than or equal to n mod an mod x naught power n divided by mod x naught power n into mod x power n by mod x. Okay, in fact, now that I think about it, this is just an equality, not an inequality at all. It's just equal to. There's no less than or equal to. Less than or equal to is unnecessarily weak. Okay, so all I have done is I have multiplied and divided by mod x naught power n. Then I have divided by x and multiplied by x. Modulus, of course. Okay, so what we are going to do now is this is less than or equal to, I'm going to club together these two terms. This is less than or equal to n m by mod x by x naught the whole power n. Okay, excellent. Now we are interested in n an x power n minus 1, and what we have shown is the modulus of the quantity inside is less than or equal to n m by mod x by x naught. I can put a big modulus, so that looks silly, so I will just put modulus x by x naught the whole power n. This is what we have. So we are going to apply the Weierstrass M-test. So it is up to us to now analyze this n m by mod x by x naught the whole power n. Okay. Now of course this is just a constant because capital M is a constant and x has been fixed. This is where that is being used. So this is less than or equal to some constant times summation n. So I shouldn't literally be writing less than or equal to some constant time, simply because I have not shown convergence of this series yet. So let's just analyze n mod x, this series, summation n mod x by x naught the whole power n. This series. Call this quantity inside, let's say r naught. What we know is r naught is strictly less than 1. We know this. Okay, so we have summation n equals 1 to infinity n r naught power n. Okay, now this series converges. Why? Well, essentially because we have an exponential and something like that grows like n, and sort of this exponential goes to 0 faster than this n can converge to infinity. You can give an argument like that and try to make that precise, but you can apply the ratio test directly. That's easier. Apply the ratio test. Applying the ratio test means you have to compute limit n going to infinity of a n plus 1. I shouldn't use a n plus 1 because b n plus 1, let's say b n plus 1 by b n, and you have to show that this ratios converge to a quantity that is strictly less than 1. Let's see what these ratios will be in our scenario. It will be r naught power n plus 1 by r naught power n, then n plus 1 by n, which is just equal to n plus 1 by n into r naught. Okay, and it is easy to see that this converges to r naught, which is strictly less than 1. So hence by ratio test, summation n equals 1 to infinity n r naught power n converges, which means the original series that we were interested in, m by mod x summation n equals 1 to infinity n mod x by mod x naught power n converges. Now by Weierstrass M-test, the series summation, and actually you don't need to use the Weierstrass M-test. I'm being bit of an overkill. Just by comparison test, no need to invoke. Essentially the proof of Weierstrass M-test can also be proved directly from the comparison test. That's besides the point. So by comparison test we have summation n an x bar n minus 1 n running from 1 to infinity converges. Okay, so this was a lot of steps that essentially reiterated something very simple. So all we needed was to show this. We have shown that if x naught is a point where the original series converges and x is there in minus x naught, then summation n equals 1 to infinity n an x bar n minus 1 converges. So if you just think about it, what we have shown that the radius of convergence of summation n an x bar n minus 1 n running from 1 to infinity is at least equal to, not at least equal to, that is really silly, is greater than or equal to the radius of convergence of summation n equals 1 to infinity n an x bar n minus 1. Okay, sorry, I wrote the same thing again. N equals 0 to infinity an x bar n. Okay, now I want to claim that the radius of convergence is in fact equal. It's in fact equal. To do that, what I do is consider the series summation n equals 0 to infinity an by n equals 1 to infinity an by n x bar n plus 1. Oh, just a moment, this is not correct. This is n equals 0 to infinity an by n plus 1 x bar n plus 1. Can you guess what this series is? Well, this series is nothing but term by term integration. Right? X bar n will just become x bar n plus 1 by n plus 1. That's why you get x bar n plus 1 by n plus 1. An remains as it is. Now, what's so special about this series? Well, observe that by a very simple argument similar to what we have done for the differentiated power series, what we have done for the differentiated derived power series star. So call this series double star. This series double star also has radius of convergence. Greater than or equal to that of summation an x bar n. Okay, If you are like me, by now you are having a migraine, but ignore the pain for a moment because the proof is almost done. What has happened is, if you do term by term differentiation, the radius of convergence is at least as high as the original radius of convergence. The same thing is true if you do term by term integration. Therefore, if you do term by term differentiation of the term by term integration, you get back the original thing. Putting all this together, the proof is done. So I'm not going to elaborate anymore because I don't have a painkiller at hand. So putting all this together, the radius of convergence of star, double star and summation a n x bar n coincide. Okay, so let's go back way back to the statement of the theorem. The statement of the theorem says that the derived power series also has the radius of convergence r, which we have now shown. And this converges to a function g such that f prime equal to g, where f is the function that summation a n x bar n converges to. Well, what you do is the following. Fix any closed interval within minus r. On this closed interval, this series summation a n x bar n minus 1 converges uniformly to g. Now apply the result about uniform convergence and differentiation, and this will follow immediately. Okay, so I'm going to leave the rest of the details to you. As you can anticipate, I'm leaving more and more stuff to you because we are at the end of this course, and by this time you should be adept at proving such simple stuff. This is a course on real analysis, and you've just watched the module on the Weierstrass M-test and uniform convergence of power series.